What is the base of log x? Normally there would be a base here, but there is no base. What is this base? So if there is no base, it's a 10. The log without a base, that's an invisible 10. It's a log base 10. So what would be log base 10 of 10? We set this equal to x, and we put it in exponent form. It's going to be 10, which is our base, to the x power equals 10. So 10 to what power equals 10? X equals 1. Hint, if your base and your argument are the same, that's always equal to 1. Log base 317 of 317 always equals 1. Okay, what about log of 10,000? So again, set it equal to x. Our base is 10, our power is x, equal to 10,000. What power of 10 is that? Count the zeros. 1, 2, 3, 4. X is 4. What about log of 10 billion? Hopefully you're noticing a pattern now. Count the zeros. 3, 6, 9, 10 zeros. That's equal to 10. What about 0.001? So here we moved the decimal 3 places. Yeah. No. 4 places. All right. 10 to the x power is 0.0001. That 3 zeros, 4 places. 2 zeros. 2 zeros, 3 decimal places. So, yeah. 0.1 is 10 to the negative 1. It's 1/10. 0.01 is 10 to the negative 2. 0.001 is 10 to the negative 3. So 3 places. Yeah. 3 places. That's going to be x equals negative 3. So then 0.0000001. 1, 2, 3, 4, 5, 6, 7, 8. That's going to be negative 8. Given that log of 7 is 0.8451, evaluate each logarithm. So we can rewrite this, right, as log of 7 times 1 million. And we can use our log rules and make that log 7 plus log 1 million. Log 7 is 0.8451. Log 1 million is 6. 6 zeros. 6 is log. So 6.8451. For B, we can write this as log of 7 over 10, 100, 1,000, 10,000. Which would be log 7 minus log 10,000. And that's going to be 0.8451 minus 4, which is going to be negative 3.1549. Drinking water is routinely tested for its pH level. The pH of a solution is a measure of acidity and is related to the concentration of hydrogen ions measured in moles per liter. If the water being tested contains 7.94 times 10 to the negative 9th moles of hydrogen ions per liter, what is the pH level of the water? So, log base 10 of 1 over 7.94 times 10 to the negative 9th. And we're probably going to want to plug that into a calculator. And so on your calculator, you have the log button towards the bottom left there. So if we do log of 1 over 7.94 times 10 to the negative 9th, we get about 8.1. So that's going to be a pH of about 8.1. All right, graph y is greater than log of x minus 4. So the parent function, y equals log of x, right? We know that log of 10 is 1. All right, log of 10 is 1. Log of 1 is equal to 0. You can't take the log of 0 or the log of a negative, and so what you end up with is you end up with a vertical asymptote along the positive x-axis, and you end up with a function. It kind of looks like a square root function. It's going to increase infinitely, but it gets pretty flat. So this is y equals log of x. Using our transformation rules, if we subtract 4 inside the log, that's going to shift the function 4 to the right. So now we have a new asymptote at y equals 4. And that's going to go through here. And so our function is going to look like this. And look like this. That said, it is y is greater than, not greater than or equal to, so this should be a dotted line here. And we want to shade everything above this. So everything above this is going to be all of this. Do not shade to the left of the asymptote because the function is not defined there. We have this change of base formula, so way back in ye olden days, before you had the log base function on your calculator, you used to have to use this change of base formula to find the base of things, to evaluate functions that had a base that wasn't log or e. So if a, b, and n are natural numbers, and neither a nor b is 1, the following equation is true. So log a of n is log b of n over log b of a. So using the change of base formula for log 9 of 1043, we could make this log, let's use the log with the base of 10, of 1043 over log 9. And so if we do this, 1043 over log of 9, and that gives us 3.16 approximately. And if you do in your calculator log base 9 of 1043, you will see that it is the same thing. Technicians at a water treatment plant determine that the water supply has pH of 6.7. What is the concentration of hydrogen ions in the tested water? So now we want to solve for the hydrogen ions in this equation. And so our pH is going to be 6.7. And so we can put this in exponential form by remembering that our base is 10. So 10 to the 6.7 is 1 over the number of hydrogen ions, or the concentration of hydrogen ions in, I think, was moles per liter. And so then we solve for H plus in this equation, which means that H plus is going to be 1 over 10 to the 6.7. which is 1.99 times 10 to the negative 7th. Uh, 6 to the 3x equals 81. We cannot, we don't know, we can't change the base here. The base is 6, and 81 is not a power of 6. We're going to have to take a log. And so what we want to do is we want to take a log with a base of 6. And so we're going to take the log, same log on both sides. Remember, we had a rule that said that if our log bases are the same and the sides are equal, then what's inside is the same. We can kind of do the opposite of that and apply the same log to both sides. Use our exponent rule. We're going to bring this 3x out front. Log 6 of 6, right? If we say log 6 of 6 equals x, that means that 6 to the x equals 6, so x equals 1. So this just equals 1 and it goes away. So 3x equals log 6 of 81, and then we can just divide it by 3. So x is equal to log 6 of 81 over 3, and you can do that change of base function if you really want to, or you can use the log base function in your calculator, and to do that you go to math and you scroll down to where it says log base, and you put the base in as 6 and the argument in as 81, and then we're going to divide that whole thing by 3, and that ends up being about 0.818-ish. And that's it for what was it? Common logs. One more section to go. Tune in next time for natural logs.